Dear students, this is your instructor of Chem 5 to 4. Hope you are well, and I'm feeling happy to get back to you again. In my previous lecture, I talked about, I've already sent you recorded a lecture on the crystal field theory. In that theory, what we learned was that if we place degenerate d orbitals in a crystal field, let's say in an octahedral crystal field, then what happens to these d? They split up. And you by now know very well they split up into two sets. One set is called T2G and the other set is called EG set. Today I'm going to give you lecture on tetragonal distortions in D1 ion in a variable crystal field. By distortions I mean there is a regular shape, for example, regular octahedral. In regular octahedral, all the metal ligand bond distances are equal. They are same. Whereas in distorted octahedral, these distances are not same. We will learn more about it soon. So what I was saying is we are able to predict the UV visible spectra of D1 ion in distorted octahedral geometry as well. When we learned crystal field theory, we learned to predict spectra of D1 system in simple octahedral crystal field. But now it is distorted. What happens? This is what, to begin with, let me tell you. Whereas in octahedral, we expect only one band, absorption band. You will now, after listening to this lecture, know it for sure that we get 3 absorption bands when D1 is placed in a tetragonal field. Well, here on page 2 of my lecture number 6, you can see it is with you already. I'm showing here regular octahedron. Here it is. All bond distance, metal to ligand, all bond distance is the same. Here it is distorted. This bond distance is longer than this one. Okay, so it is elongated in Z direction. This is another distorted. Now this is compressed. The top of this is compressed down. So this is distorted, this is distorted, this is regular. I have shown it up there. This distance, okay, this distance is longer than this equatorial distances. 4 equatorial distances are equal. These 2 axial bond distances are longer and equal. This is compressed. Next, on next page, it is again the same thing. So, compressed, regular octahedral, elongated, and the number of absorption band absorbed in the distorted octahedral complex is always different from that observed in case of regular octahedral complex. When D1 ion is placed in a tetragonal environment, meaning distorted, environment, not regular, then the ground state configuration would be EG. Okay, I will, and the excited state configurations will be this: A1G, 1, B1G, and B2G. Okay, let me first of all explain you where from these are coming. Okay, so okay, wait a minute. Okay, note this A1G, B1G, B2, you are not very familiar, I know that. These are group theoretical notations. You will know more about these after learning introductory group theory. Hopefully, I will be sending you notes on this in next week. In crystal field theory, two symbols we use. You are familiar with these. One was T2G and the other was EG. Now, T2G, T stand for 3, triply degenerate. Okay, supposing if there is one electron and this is the T2G orbitals, this one electron can be arranged in 3 ways. One is this way, here, same electron here, second way, same electron here, third way. So that's why it is called T. Here is electron in the EG set, one electron. This electron can be arranged like this, one way and second. So E stands for 2, doubly degenerate, and T stands for 3, triply degenerate. Okay, there are 6 other commonly used group theoretical notations. I have put them here. Please go through these and you have to kind of remember these as it is. I've made it in a very simple way. A, as I said before, is one-dimensional, singly degenerate. Okay? There is no other way. There is only one way we can arrange that. So it is 1. Similarly, B also 1, singly degenerate. Okay? There is only one way of arranging it. E, I have already explained 2 ways, and that is why it is 2, T, 3. And subscripts I have written here. Please read it. Don't get get scared of details of these symbols. They will become more clear when I teach you introductory group. Now I come to the point. It's very easy, don't worry about it. Spectra of D1 system. Where? In regular octahedral. When D1 is put in the regular octahedral, what happens? And how many bands we expect? When it is weakly distorted octahedral, okay? Then what happens? How many bands we expect? When it is strongly distorted, what happens? And how many bands we expect? So here I have written myself. So D1 ion in Tetragonal distortion. Here is a regular octahedron where all bond distances are same. So here is T2G set, 1 electron, and so this configuration ground state will be T2G1. And when we shine light on it, give energy, it is excited, goes up there. And now its ground state or excited state will be EG1. So transition will go from T2G to EG. And there is expected only 1 band. And we see only 1 band. This is the beauty of this whole thing, that we can predict what is. Now, this is distorted octahedral. It is not a regular octahedral. In this, I have shown it here. This axial distance A and equatorial distance B, A is longer than B. A is greater than B. So what happens? When this ligand goes away, further goes away from the center, so that means this orbital, whatever that orbital is, that is dz square orbital, it is stabilized. Okay, it becomes cool, okay, less hot, so it will come down. So this is what it is. To begin with, same energy, and then this dz square, it comes down, and this, the other orbital, x square, y square, it stays up. Similarly, dxz and dyz, okay, since z distance is increased, so they also stabilize, come down. Now you see, this becomes the 2 orbital with 1 electron here, so its symbol will be Eg. So ground state will be Eg1. From this ground state, there will be a transition from here to here. Its name is B to G. Okay, one transition. Okay. Second, from here to here, second. Okay, that is from Eg ground to A1G. Fair enough. And then there will be third, Eg1 to B1G. B1G up there last. So we expect 3 transitions, and therefore we expect 3 bands. Well, let me tell you, you can see literature, you can see net, you will always find out what statement I'm making, it is exactly the same way. Okay, we get 3 bands, and those are mu1, mu2, and mu3. For what? For D1 in octahedral, distorted octahedral. Now I'm putting it in strong tetragonal distortion. That means this is strong distortion. This distance becomes very large. This L ligand goes way away from it. When this goes away much longer, then what happens? It just remains like a square planar. Okay, that means this dz square orbital, it must go down further down in energy, and this is what it is. See, this dz square was in weak distortion, it was here, and now what is happening? It has gone way down. Now the ground state is A1G, and then from A1G to EG, from A1G to B2G, and A1G to B1G. 3 transitions. I have shown them here. And so both in strong tetragonal dissolve and in weak we get these. Note, this diagram which I have given in the previous pages, A, B, C, are also okay for D9 system. D9 system is copper ions, copper sulfate, remember. And you already learned whole formalism. Dn is equivalent to D10 minus n, or D1 is equivalent. That means whatever number of D1 will give, same number D9 should give. So we can very safely predict D9 in strong tetragonal distortions, and in tetragonal distortion field it will split as follow. Okay, it is same way as D1 splitted. Okay, ground state, and then these are 3 excited states. Now here is some problem which is different from that one. From this state in D1 case, when it went here, it was empty. Okay, now it is not empty. It is full to its capacity 2 electrons. So no transition will take, okay, here from this orbital to this orbital. That means no transition will take from EG ground state to B2G, okay, Same way, no transition will take place from EG4 to A1G, okay, because this is already full. The only transition which will go is mu3 from here to here. See, it has a capacity of 1. So only mu3 is possible. The other fields are not. Splitting of d orbitals in octahedral field, splitting of d orbitals is distorted. The number of absorption band observed in distorted octahedral complexes is always different from, we learned it before, but when D9 is placed in tetragonal environment, ground state configuration will be e.g. I explained you just now, and there will be these 3 excited states. See the diagram on page 8. Okay, now diagram on page 9. This is wrong. Okay, please change it. Page 9. Unlike D1 case, only one transition from ground state to B1G is possible, and that's all. Okay? Others are not. Reasons are given in the table here below. Not allowed, P2G orbital is full. Okay, not allowed, A1G orbital is full to capacity. Okay, B1G, okay, half filled. And so what you do? You get in D1, your copper. Okay, case, you get only one band. And we get one band, and that's all. God bless you. Okay, you are learning absorption spectra of transition metal complexes, and by now I think we have we have started how the spectra should come and whether it comes the same way or not. We are capable of predicting it. God bless you.